All right, this is a short presentation about Diffie Hellman. Diffie Hellman's, hey, you guys listening back there? No. This is a key exchange protocol. All right, very short. So here's how it works. We have Alice and Bob. They share a Diffie-Hellman key group, a large prime number, and integer G. Okay, they share these. Okay, Alice normally chooses P and G and then shares them with Bob. Okay, this will make sense in a minute. Alice generates a random number, large random number X, and sends the half key to Bob, and Bob does the opposite, generates a large random number Y, and sends the half key apart. What this is allowing us to do is share a common number without sharing the whole entire number. We're sharing a portion of it, but it actually makes it work. Okay? Here's how it actually works. So Alice and Bob compute a key. So we basically shared this part at the bottom here. They generate a large X and a large Y, and they share their half key. Okay? What this gives us, and I'll show you, when I show you the math, you're going to be like, that's all it is? It's that really that easy? And it really is. Okay? The advantage of doing this is as long as the key is strong, or a long string, that's how good the key ends up being. Neither Alice nor Bob know the entire thing, so they can't sabotage it. So we couldn't sit there and Alice or Bob couldn't mess it up on anybody. Disadvantages, how do you know you're actually working with really Alice or really Bob? You don't know that. No replay and no denial of service prevention. Now let me show you the way it actually works. Okay. This is what you'll see on a test, by the way. Okay. So consider a Diffie-Hellman scheme with G of 3 and P of 353, where Alice and Bob pick 97 and 233. Okay? Complete the half keys, X and Y, and the key K. Okay. I give you all this right here. Okay? And the math is incredibly easy. So X is G to the X mod P. Okay? And we know those because G is 3. See that right there? G is 3. So G, we put it in the 3. And we take the X, which is 97, so it becomes 3 to the 97th, mod 353, which becomes 40. Then we use the same G. Remember, one of them picked X and one of them picked Y, so now we're doing 233, mod 353. Because the 97 and the 233 are the two that they don't know about right now. Okay? Then the key is the rest of it. You take the X you calculated, and in this case up here it's a 40, raise it to the Y, and in this case it's 233, the same Y you used right here, mod 353, and you get 160. Now the other half of the key, again, if you take the Y, which in this case was the 248 raised to the X, which we know was 97 right here, mod P, which was 353, we get 160. So the X and the Y were never shared, but the results come out to be the same. That's all the math there is to it. It's that simple. Okay. So what ends up happening now is Alice and Bob both have 160, yet neither one of them knows the full way they got it. You know what I mean? Because like we said here at the beginning, Alice would pick the 97, and Bob would pick the 353. They don't have to share those. So they work together. Okay? Once you do a couple of them, they're very simple. And that is literally all the math there is to it. You can do this math right here, which is X is equal to this, Y is equal to this, and then there's the key. X to the Y mod P, Y to the X mod P. Now when doing this, what do you think happens if you do this and one of these K's are different? You did something wrong. So I recommend do it both ways to kind of check your work. I don't know if I'm making you do it both ways. Did anyone look at the practice assignment already?
I did.
Did it ask you for both keys? I can't remember if I did or not. Okay. But
because it's multiple choice.
Oh, okay. Yeah. Do you like it better multiple choice?
A little bit. We like it better than people's multiple choice.
But the multiple choice, I mean, obviously the right answer is there. So, and I wasn't real tricky on these. I was tricky on some of the other ones. This one I wasn't really tricky on. So,
X and Y are the half keys, right?
yes. These are the half keys at the top. These are the half keys. Then you use your half key with the number you had, either the 93 or the 233, to calculate the whole key, and they will match. Obviously, these are small numbers, so they don't do a lot for us, but if they were huge numbers, they would do the same. Okay? So it's just a way of sharing some things, but not all, to get the same results. They work perfectly. Okay? Here's another one. So consider Diffie-Hellman scheme where G2, P11, where Alice and Bob pick X is 6 and Y is 8. Calculate them. There they are. These are much smaller numbers. So X was 6, Y was 8. So we go G, which was 2, so 2 to the 6th and 2 to the 8th. Mod 11, we get 9 and 3. Very basic math. Then we use that 9 and the 3 in the bottom part. So we're using the 9 and the 3 along with that original X and Y. See that original X and Y is being used again, along with those half keys, mod 11, and you get the result. Okay? Very basic math. You shouldn't have any problem with this at all, because the formula is very short. Okay? All right, that's all for Diffie-Hellman. It's a very short one. Please walk through